We are recording, and I do have audio. Someone just came in, needs to sign the sheet. Here you go. So let's start with questions from the homework. Dalton. Okay. Let's. This is a Coulomb's law problem. Start with the magnitude of the force. It's going to be equal to K times Q1, Q2 over R squared. Somebody look in their book and make sure that I got that right. Okay. What is K? 9 times 10 to the 9 Newton meters per Coulomb squared, right? Okay. That's K. Q1 is 25 times 10 to the minus 6 coulombs. Times, what's Q2? Coulombs. Divided by, what's the distance between them? 16 centimeters. So 16 times 10 to the minus 2 meters squared. Coulomb squared cancels here. Meters squared will cancel here. That'll leave newtons. So, put in the numbers. What numbers do y'all come up with? $3,000. Is that what anybody else coming up with? It is what you got? I haven't gotten anything yet. Yeah, I'm coming up with something different. How much? 0.65625, yeah. You used 8.998 times 10 to the 9 for K, or 9 times 10 to the 9 for K? Okay. Yeah, but 2,200 or 22,000? Okay. Yeah, 21,972.65 or 0.66. So yeah, to how many significant digits? 2 and 2. So to 2 significant digits, it would be 22,000. There's any more questions from the homework? Has anyone finished the homework? Has it ready to turn in? No? Then this is not a good start to the semester, so let's work some more of these homework. Get your pads and get your notepads and your pens ready. Get your calculators ready. I ain't doing the arithmetic for you too. Say again? Your book hasn't come in yet? All right, well, you took notes on that one, right? Okay. What did you get, Dalton? What did you get for number 1? The magnitude of the electric force of attraction between an iron nucleus. How? Yeah, number 1. Yeah. Still, it's the charge of the electron at the lowest orbit. Okay. And you came up with what for your final answer? Everybody else punch in the numbers and see if that's what you get. Actually, it specifies the direction in the problem. It says what is the magnitude of the force of attraction. No, you're right. It asked for the magnitude. I'm telling you, it specified the direction. Did everybody else get this same answer? Anybody get something different? Cyrus? Deb? All right. Who wants to volunteer? Come on, I'm going to help y'all do your homework. I need volunteers to come up here and help me do it. All right. Number 2. How many electrons make up a charge of minus 48.0 microcoulombs? How many electrons is that? But how did you get it? Divide this, 48, actually they're both minus, which cancels out. 48.0 times 10 to the minus 6 coulombs by this many coulombs per electron. The coulombs cancel, the 1 over electrons becomes your unit, and that gives you how many? You actually round it. Punch a number in your calculator and look at what does that round to 3 significant digits. So if you were rounding that to 3 digits, what would that be? .00. It rounds up the next one, and that rounds it up. So. Okay, who wants to do number 4? Everybody's getting the benefit. Don't everybody leave it on Dalton to help. Good, we got a volunteer. Come on up front. Number 4, what is the repulsive electrical force between two protons that are 4 times 10 to the minus 15 meters apart in an atomic nucleus? Yep. Where do we start? Yep. We're using Coulomb's law. It would be the same charge both times. They're both 1e charge, or 1.6022 times 10 to the minus 19 coulombs, but they're positive. Separated by what distance? 4.0. Yep. Square. All right. How many significant digits will be in our answer? 2. Somebody do the arithmetic. Two significant digits. 14 newtons. That's how hard they're pushing each other apart. Okay. Did anyone do number 5? All right. Well, let's. Oh, yeah, because we definitely need to get to 16. We've got an exam. What? This is week 2. I think our exam is next week, isn't it? Somebody, I'd have to look on Canvas to make sure. Next Wednesday or Monday? Well, at any rate, you're definitely going to want to have done number 16. But we'll get there. No, number 16 in this problem set. Oh yeah, chapter 16 exam. All right. So, we have a plastic cone charged by rubbing it with a cloth. if it is charged, if the charge it's holding is 3 microcoulombs of electrons, and it's the mass of the comb to begin with is 9 grams. Is that right? Yeah, 9.0 grams. And it's charged up to 3.0 times 10 to the minus 6 coulombs. Three microcoulombs. What's the percentage change in the mass of the cone? How would you calculate that? How would you calculate the percentage change in the mass of something? Start off, you take a Tonka toy truck, weighs 50 grams. That may or may not be right. I don't have any idea. But you add 10 grams of sand to the bed of the dump truck. What's the percent increase in the weight and the mass of that truck? Well, actually, you're adding 10 grams to 50 grams. So the part that you increased divided by the sum. Or actually, I guess you could just start with the total. These things can be ambiguous. If you're starting off with 50 grams, how much are you increasing that 50 grams? So it'd be 10 divided by 50. What percentage of that 50 grams is 10 grams? Now, if you ask, what is the percentage of the load what is the percentage of the mass, the total mass, the load to the total mass, then it would be 50 plus 60 in the denominator. Okay, but in this case, we're asking here, we have a 9-gram cone, and we're adding 30 microcoulombs worth of electrons to it. So, first thing you got to know, how many electrons is that? So, how many electrons is 30 microcoulombs? I'm sorry, 3.0 microcoulombs, or exactly. Look at you were starting to ask. Look at your units. 1.6022 times 10 to the minus 19 coulombs per electron. Well, the coulombs cancel and the E flips up. So this would give you how many electrons? Times, bingo, 1.9 times 10 to the 13 electrons. But don't clear out your calculator yet. That's correct to 2 significant digits. But we're not finished doing the calculation yet. So when you're doing a multiple calculations, one on another, Do not round every time. Don't keep all of the digits in your calculator until you get to your final answer, and then just round your final answer to the number of significant digits. Otherwise, every time you round, you introduce a little bit more error. So, that's how many electrons we have. What is the mass of each electron? Inside your front cover. That sounds right. 1.9 times 10 to the 13 electrons times 9.11 times 10 to the minus 31 kilograms per electron equals how many kilograms? .71 times 10 to the minus 17 kilograms. So actually, it would be 1.70 to 2 significant digits. Now, what percentage of 9 grams is that? Very. We ain't there yet. So every one of you is making a mistake as we speak, right now. No, you have to convert the grams to kilograms. You can convert either, actually, but you've got to convert one to the other, or you don't get the right answer. You got to make sure your units match. 9 grams is how many kilograms? Times 1 kilogram for 1,000 grams, so 9 divided by 1,000 0.009 kilograms. So we divide this by 0.009. Now what do we get? You divide the increase by the total mass that you're added to, and that'll give you a percent. That'll actually give you a ratio of an increase. Times 10 to the minus 15 is your ratio. Now to get it into a percentage, you got to move that exponent 2 more places, 2 more decimal places. So multiply that times 100. And you end up with 1.9 times 10 to the minus 13%. Okay, here's another good one. Number 9. What is the total charge of all the electrons in a 12 kilogram bar of gold? Now, part B. What is the net charge of the gold bar? So I'm going to start with part B. Somebody tell me the answer to that right now. It's the net charge of the bar of gold. We're on number 9. 2 parts. Part A, what's the net total charge of all the electrons in a bar of gold? And they tell us that, they give us some data about gold. It has 79 electrons per atom. And that it has the mass of each atom is 197 daltons, or atomic mass units. The dalton is actually a unit. It's strictly speaking, it's a mass to charge ratio. It's a unit of mass, atomic mass divided by atomic charge. Yeah, as soon as you find a girl somewhere that gets all hot and bothered over a mass spectrometry, you got it made. No, I married her, so back off. So, how do we go about solving this problem? A. Okay, well, let's find out first of all. 12 kilogram bar of gold. So, A, total charge of all the electrons in the bar of gold. And B, net charge of the bar. So start with B. What's the net charge of that whole bar of gold? This really shouldn't be a trick question, folks. It is. The net charge it's neutral. It has the same number of protons as it does electrons. So the net charge is 0. It's neutral. If you added some electrons, or if you stripped some electrons away, exactly, then it would have a net charge. But as long as, until and unless you ionize some of those atoms, every atom is net neutral. Same number of protons as electrons. Now, of course, that still leaves us with the actual problem. How many electrons are in 12 kilograms of gold? We can. We know the mass of an electron. We know that every electron in that bar of gold weighs, and I know that's not quite the proper term, but 9.11 times 10 to the minus 31 kilograms. Does that help us? Do we need to know that to solve this problem? What we need to know is how many electrons there are. And we know that there are 79 for every atom. And we know that the atomic mass of an atom of gold is 197 AMU, or U. On the inside cover of your book. Under fundamental constants, right there at the very bottom. Atomic mass unit, 1U. 1.6605 times 10 to the minus 27 kilogram. 1.66 what? 0505. 27 kilograms for every U. What does that tell us when we multiply this number, this 1.66 times 10 to the minus 27 kilograms times 197? What does that give us? It gives us, first of all, do the arithmetic. What does that give us? Kilogram. Yeah, we're gonna hold on to the extra decimal places until we get to a final answer. Avoid as much rounding error as we can. But this many kilograms is what? That is the mass of each gold atom. No, we're still just looking at, what do we know? If you look on the, where's gold on this periodic table here? There it is. Sixth row just to the right of the center. Anybody got anything to add yet? That's how many electrons there are in every atom. That's the mass of the atom. What we need to determine is how many atoms are in 12 kilograms. How many atoms of gold would be in a 12 kilogram bar? So, I would do it. 12 kilograms per atom, or that many kilograms per atom. So if we divided the number 12 kilograms by that mass, that would give us the number of atoms we have. We would, exactly, we have this mass, this many kilograms for every atom. Now, if we have 12 kilograms to begin with, we divide 12 kilograms by that number, call that again, please. That's how many atoms are in 12 kilograms of gold. There we have 79 electrons on each and every one of those atoms. So we take that number and multiply it by 79. There's where we use the 79. Yep. Electrons. Now, how many coulombs are each one of those electrons? Times 10 to the minus 19. Exactly. So we multiply that number, but it's actually 2.90 times 10 to, yeah, don't round it yet. 2.898, etc., times 10 to the 27 electrons times 1.6022 times 10 to the minus 19 coulombs per electron. And that gives us what? $464 million coulombs. If you could move that many electrons past a point in a wire every second, you would be pumping 464 million amps. There's a lot of electrons in 12 kilograms of gold. Okay. For every one of those atoms, you have 79 electrons. And then multiplying that number of electrons times 1.6022 times 10 to the minus 19 coulombs for each electron. Got this many electrons times 1.6 022 times 10 to the minus 19 coulombs for every electron. Those cancel out, and you're left with 464 million coulombs. Or we had 12.0 kilograms, and so that would be our significant digits. That's the charge of each electron. Actually, it's minus 1.6022 for electrons. It would be plus 1.6022 for protons. And if you were going to actually do the math to answer part B, you would say, well, I have that same number of atoms that I have for 79 electrons each, but I also have that same number for however many electrons I have the same number of protons, but therefore they have plus 1.6022 times 10 to the minus 19 coulombs per proton, because they're positively charged. So then when you multiply that out, you've got this 464 million coulombs of protons plus minus 464 million coulombs of electrons equals 0 net. So you end up with net neutral, with no charge. Does anyone have any questions what we've done so far? No? Everybody's keeping up. All right. I don't think we're going to get to do all of your homework. We definitely need to do some more. We need to talk about electric fields before we start the lab on Thursday, because this is, seriously, do not miss lab this week. I don't care. This is not a lab you will be able to make up. Okay? This is going to be a tedious, time-intensive, labor-intensive, data analysis, sitting there with your calculators, crunching numbers, calculating vectors. We are going to plot a vector field. I'm going to get y'all started real good on it. And y'all will finish it up as a take-home lab over the course of the week, and then bring it back. And we will use the same plot, the same graph that you make in this week's lab will be used in your week 3 lab when we look at equipotential, when you actually measure some equipotential surfaces. But there will still be time for that on Wednesday. So let's see, where did these questions go? We've done 9. 10 is compare the electric force holding the electron in orbit around the proton of nucleus of a hydrogen atom with the gravitational force between the same electron and proton. Do y'all remember how to calculate universal gravitational constant? You know how to use the universal gravitational constant. I don't remember what it is. We can find out. 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. But it's the universal gravitational constant, m1, m2, divided by the distance between them squared, is the force due to gravity. If you take this universal gravitational constant, the radius as the radius of the Earth, and m1 as the mass of the Earth, that part equals 9.8 meters per second squared, or 32 feet per second squared. Okay? This is how you would calculate the gravitational attraction between any two objects. You just got to know the two masses, the distance between them. You can calculate the force of attraction due to gravity. You've also got the Coulomb's law. Which looks suspiciously like it. That's what you'll need to use to do 10. And you can get the gravitational constant G. It's the second line under fundamental constants on your inside cover. All right. 13. A charge Q is transferred from an initially uncharged plastic ball to an identical ball 24 centimeters away. The force of attraction is then 17 millinewtons. That means 17 times 10 to the minus 3 newtons. That is equal to what? This is Coulomb's law again. You got K times the total charge that was transferred, which is minus Q, however many electrons got sucked away. If the ball is initially initially neutral and you suck off minus Q electrons, what's the net charge of the ball left behind? Plus Q. You've got two balls, plastic balls. They're both electrically neutral. You suck off minus Q worth of electrons from this ball and deposit them on here, so this one becomes minus Q charge. What does that leave for charge on the original ball? Plus Q. So you've got this 17 millinewtons is equal to K times negative Q times positive Q times divided by the distance between them squared. Well, and then you will solve for Q, which is essentially just you're going to solve for Q. That'll give you the total charge that was transferred. But look at the question. Read it carefully. What are they asking you for? They're wanting to know how many electrons were transferred. Once you've solved for Q, that's your total charge. Divide it by the number of coulombs per electron to give you the number of electrons. 15. At each corner of a square of side L, there are point charges of magnitude Q, 2Q, 3Q, and 4Q. And they're all L apart. This is just algebraically manipulating the Coulomb's law, and we will do number 16 before we start class on Wednesday. And I'm out of time. Class dismissed. Seriously, do not miss lab this week. This is a big one.